Okay, so this video is going to go over the practice test for the second IA that's upcoming this week, on Wednesday for you guys. If you don't have a copy, I'll send it over digitally to you guys along with the video link to this. And I'm going to apologize ahead of time for my voice because I am recovering from a sore throat this weekend. So bear with me, guys. And if you hear any weird background noise in this video, that's probably because I'm watching Sherlock in the background. Yeah, so let's begin. Okay, so number one, we have two stones thrown horizontally from the top of a cliff. One has 15 meters per second speed, the other one has 30 meters per second. We gotta compare the time it takes for them to reach the ground. And so you should know horizontal projectiles, that means they only have horizontal speed initially. And here we're dividing both horizontal and vertical directions. In the horizontal direction, the speed only affects the horizontal distance, whereas the vertical height that it stands from, the height, also adds onto the airtime of the object. So to increase the height, you increase the airtime of the object. The horizontal speed has nothing to do with the airtime. And so since they're from the same height, they're going to have the same airtime. Choice A. Now number two, an object is dropped from rest, falls freely 20 meters to earth. When is the speed of the object? 9.8 meters per second. So we're looking for time when our final speed is 9.8 meters per second. We're starting from rest, 0 meters per second, and our distance is 20 meters. So let's list our variables. This is a 1D kinematics problem, going free fall. Okay, so after you list your variables, we can figure out which equation we can use. VF equals VI plus AT, because we're looking for the time it takes to reach that speed. And so you should get T is equal to 1 second, approximately 1 second. And you can also think about it logically what acceleration means. So 9.81 meters per second squared. So each second that passes, the object gains a speed of 9.81 meters per second. So each second that passes, the speed of the object increases by that rate. Okay, so each second it increases that much. Alright, and then number three is almost applying the same idea from number two. How much time will it take for it to reach 30 meters per second, starting from rest, using the same acceleration, 30 meters per second divided by 9.81 meters per second squared. It follows the same equation that we used in number two. And you should get that it's approximately 3 seconds. And then number four. So this one is more tied with potential energy and kinetic energy, which we haven't covered yet, but we can still use a little bit of kinematics to solve this. I'm not going to require you guys to focus on this question. So anyway, so a book of mass M falls freely from rest to the floor from the top of a desk of height h. What is the speed of the book upon striking floor? So the way I went about it, I used this kinematic equation because it has a speed that we're looking for, initial velocity, acceleration, and distance. So we could plug it in. A is equal to G, 9.81 meters per second squared. D is our height, our vertical height. And we're looking for VF. We know that VI is 0, so because it starts from rest. And we just solve for VF in terms of the variables, and we just get radical 2GH, choice A. Alright, so 5, 6, and 7 will be shown here. Number 5, what is the speed of a 2.5 kilogram mass after it's fallen freely from rest over a distance of 12 meters? Here we're going to ignore mass and focus on the kinematics aspect of this. We're looking for the speed VF, fallen freely from rest, so acceleration is 9.81, initial velocity is 0, distance is 12, use VF squared equals VI squared plus 2AD, plug and chug, and you get 15.34 meters per second, and that is choice B, approximately 15 meters per second. Alright, number 6. A 5 kilogram sphere starting from rest falls freely 22 meters in 3 seconds near the surface of the planet. So this is a different planet other than Earth. So we should know that our acceleration 9.81 is not going to apply here. So we're going to compare this new acceleration due to gravity to Earth's. And so you solve for this new acceleration given our variables VI, D, T, and we're looking for A. So we can use this equation, D equals VIT plus 1/2 AT squared, plug and chug, And you get that A is approximately 5 meters per second squared on this planet, and it's less than 9.81. It's about half as great. So that's choice C. Number 7, another free fall question. A rock falls from rest, vertical distance of 0.72 meters, surface of the planet, 0.63 seconds. Again, we're not on Earth, so it's not 9.81 meters per second squared, so we're going to solve for this new acceleration. VI is 0, D is 0.72 meters, T is 0.63 seconds, and we're solving for A. Use the same equation that we did in 6, and A is equal to 3.63 meters per second squared. Alright. How are you guys holding up so far? It's a lot of kinematics so far. Don't worry, dude. Forces are coming up. Alright, number 8 right now is going to be our last kinematics question for now. So number 8, how far will a brick starting from rest fall freely in 3 seconds? Pretty straightforward. How far is distance? We're looking for VI, start from rest, 0. A is 9.81 meters per second squared, and T is 3 seconds. Solve for D, and you get approximately 44 meters. Number 9, now we're on to forces. Which person has the least inertia? So here inertia is related to mass. So least inertia means least mass, and that's choice D. 50 kilogram girl. It doesn't matter the speed. The speed is not affecting inertia. Inertia is only affected by mass. So forget the speed. Focus only on mass when it comes to inertia. Alright, number 10. Which situation represents a person in equilibrium? So when we're in equilibrium, the object can be either at rest or constant velocity. And so we're looking for situations that show either at rest or constant velocity. And here, the only one that shows that is choice C, a man standing still on a bathroom scale. Alright. Number 11 follows a similar idea. In which situation is the net force on the object equal to 0? 0 net force means equilibrium. Again, at rest or constant velocity, the only one that shows that is choice C, moving at a constant speed. Number 12 shows motion graphs, and we're looking for one that shows an object in equilibrium. So we're looking for constant velocity or at rest. So here I'm listing what they are for choices A, B, C, and D. A and B show acceleration, C is constant velocity, and D shows momentum over time. So don't worry about that. We didn't cover that at all yet. So the only one that's valid here is choice C. Number 13, here we have two objects and they experience the same unbalanced force. But because of their different masses, they're going to experience different accelerations. So applying Newton's second law, F equals ma, you solve for that force, apply to the second object, and you get A is equal to 6 meters per second squared. Alright, now let's go on to number 14. Here we have a diagram. Acceleration follows the force. So if F1 is greater, it's going to follow more towards the right in the direction of F1. So accelerating in the direction of F1, choice C. Number 15, an object with a mass of 2 kilograms is accelerated at 5 meters per second squared. The net force acting on the mass is, so a simple F equals ma scenario. You plug and chug, solve for F. Our mass is 2 kilograms, our acceleration is 5 meters per second squared, and 2 times 5 gets you 10 newtons. And whoa, the guy just, whoa, I don't know what's going on here. Oh my god, someone just shot himself in the head. Yikes. Sherlock is crazy. Alright, number 16. A 100 kilogram cart accelerates at 0.5 meters per second squared west as a horse exerts a force of 16 newtons west on the cart. What is the magnitude of the force that the cart exerts on the horse? Okay, so after I drew this whole diagram, I realized it's pretty pointless because this is really an application of Newton's third law. So action, reaction, same force, opposite in direction. You gotta focus on the wording here. If the objects that are interacting are still the same in the question, then it's the same force. So horse on cart, cart on horse, same force, different direction, 60 newtons. Alright, that's number 17, which diagram represents a box in equilibrium. So we're looking for balanced forces. The only one there is choice C. Alright, number 18 is a huge loaded question, an ice skater. Alright, I'm not going to go on and rant about ice skating right now because a big competition just happened this weekend and I have mixed feelings about the results. But anyway, so we're here, let's draw our diagram. 20 kilograms. And we have our forces left and right. Force being applied to the right, frictional force to the left. And here, we're also given a mu value, 0.28. We're accelerating to the right, 1.4 meters per second squared. Our up and down forces are weight and normal force, where those two forces are the same. They're always the same in our problems. And so here, we're looking for the force applied on the block. But to get there is a lot of steps. First, we need to figure out our force of friction. Here, we're mu times F of n. The normal force is also the same as the weight, so you can either solve for that separately and plug it in, or you can just do it in one go like I showed here. So 0.28 is our mu times mass times g, 20 kilograms and 9.81 meters per second squared, and you get 54.94 newtons as your frictional force. Now this is acting opposite to the force applied. In our scenario, because we have an acceleration, these are not equal to each other. So do not make that mistake of setting them equal to each other because we don't have an acceleration. Because in this problem we do. So we have to solve for our net force, F equals ma. 20 times 1.4 gets us 280 newtons as our net force. So the difference between the left and the right side is 280 newtons. So we need to find what F is now using that. So if 280 is the difference between our force applied and our force of friction, we set it up this way, and you get 334.94 newtons as your applied force, and that's your answer. Alright, number 19, we have a soccer ball kicked at a certain speed at an angle above the horizontal level ground. It's a simple question, just sketch the path of the ball's flight from its initial position P until it returns to level ground. So it should look like this. That's it. And here I'm just going to add some little detail just for whatever. Right, number 20. Here, similar to what we've been working on a lot lately, so horizontal force of 8 newtons is used to pull a 20 newton wooden box to the right, as shown. So 20 newtons is our weight of the box, and this is also equal to the normal force going up. Simple question, we just gotta draw the normal force vector. I'm clearly not gonna draw this to scale, but so you know, 5 centimeters is our ratio there. 1 centimeter equals 4 newtons, so we have to draw a 20 newton vector that is 5 centimeters in length, and that's definitely not 5 centimeters. Probably a lot longer than that. Anyway, next set. 21 to 23. Alright, so you gotta use a ruler to measure that scale diagram. So based on however you measure in whatever centimeters or inches, it should come out to about 9.33 newtons. I use centimeters. And the net force here is the difference between the left and right sides because they're unbalanced. 2.67 newtons is our difference. Solve for acceleration, F equals ma, carry that F net over. 2.67 newtons is equal to 4 kilograms times A, and A is equal to 0.67 meters per second squared. Whew. Number 24. Another inertia question. Compared to 6 kilograms of lead, 8 kilograms of feathers has more mass and more inertia, even if it's feathers versus lead. Alright. 25. Greater net force equates to greater acceleration on the object, so we're looking for one that has the most unbalanced net force. B and D are all balanced. C has a top and bottom balance, and all we're left is a right force that is unbalanced of 1 newton. And choice A has has a down and a rightward force together. They make radical 2 newtons going down to the right. Alright. Number 26, another motion graph question, has an object with no unbalanced force, so we are, with no unbalanced Alright, yeah. So we're in equilibrium. Had to question my wording of it, my answers. No unbalanced force. So we're in equilibrium, at rest, or constant V. The only one that fits is choice A. B, C, and D are all acceleration. Alright. Number 27. Newton's second law. Same force across each of the object. If you apply the same force to all the objects, the ones with the greater mass will experience the least acceleration. So this is an inverse relationship between mass and acceleration if you have the same force. So 4 kilograms, choice D. 28. Here we have a diagram with 4 forces acting on it. Sorry guys. 120 to the left, 100 to the right. These are the only pair of unbalanced forces. Total them together, you get 20 to the left, and so it's going to accelerate to the left. Number 29, here is an application or problem-solving version of that question. So 25 up, 35 down. Net force is 10 newtons going down. Using our mass of 15 kilograms, F equals ma. Plug and chug, 10 newtons equals 15 kilograms times A. A is equal to 0.67 meters per second squared. Whew, mouthful. Alright, now the last question. There's a lot. Alright. Oh no, 2 more questions. Hey, a familiar question. A baseball bat exerts a force of magnitude F. Alright, this is Newton's third law. Same force, opposite direction. So we're still looking at the same interacting pair of objects. Ball and the bat, same force, but because they have different masses, they experience different acceleration. But this question is only asking about the force, so it's the same. 31, once again, is F equals ma. 0.5 kilograms times 3 meters per second squared. Calculate the magnitude of the net force. 1.5 newtons should be your answer.